Hi, Britan.
Okay.
Okay. So,
So actually, since Aditi and Soumya was in the same project, that is teleportation, so she is not, I think, seen the message or the mail. So how to do it? I mean, uh, we,
that's fine. Like, we can proceed with Aditi, and then Soumya can watch this recording later. That is also fine.
okay, okay, then that's okay. I think. Aditi, are you there?
Yeah, yeah. Yeah. I hope I'm audible.
Okay,
Yeah.
okay,
Okay.
Akshay, you can proceed.
Yeah, just give me a sec. So, okay. So we have one more session planned, right? That.
No, actually, Tavish and Tulsi both told that they have some work or they are busy with something. So only we have like this teleportation session only.
Okay, sure. Let me share the screen. So I have joined from this. We have the doc shared on the Slack, right?
Yes, I think we have shared that with Aditi.
The
Have you
Python
gone
file?
through it? Yes.
Yeah, yeah, I've gone.
Okay, okay. Let's go through that document itself. Then we'll proceed with the code.
Okay.
Okay. So, yeah, so this is the basics of the teleportation first. So we'll proceed with the stuff that is actual project after this. So it is based on this like concept only. So what exactly the teleportation is, if you look into is, we are sending a state from Alice to Bob, a single qubit state, and that
Hmm.
is for demonstration purpose from Alice to Bob, using a quantum phenomena called as entanglement. So how it exactly does it happen is basically using the circuit. So at the start, Alice has her state that she wants to send to Bob. So that state is generated by psi here, and then there is an entanglement state, the Bell state shared between an Alice and a Bob. So that Bell state, we are like there are four Bell states, so we are assuming the state to be in the first, like 1 upon root through root 2 0 0 plus 1 1. So that is the state in zero and basis we are taking. It can be any state, minus minus plus plus basis also you can write, or it can be the second Bell state, third Bell state. But we are for consideration purpose taking the first Bell state. Then what we are basically doing is applying this. So first is the C naught gate. So if you know the exact state, how the exact circuit, how the Bell state is created, this circuit applying the first C naught gate and then the Hadamard gate is exactly reverse of that. So what this operation basically does is at so you can for exclusively visualizing what is the quantum state or what is the operation happening after each unitary application, what you can do is draw a line and then write the state itself. So since this Alice states, like Alice state psi and Alice entangled qubit is separated by a distance, let's say d, from Bob, so that distance is not represented here, but that in quantum like representation, what we can do is for taking that whole space as a single Hilbert space, what we can do is tensor product, as in this psi state is first tensor protected with the second state that Alice has, and that is tensor protected with the state that Bob has, to get a three state system, as in three qubit state system. So that state after like a, for a you can write what that a state will be, the state Alice wants to set into. So I don't have a cursor because I'm like from speaking from a tab. So it is fine with you, right? You'll be able to understand what exactly is, like what exactly is the thing that I'm pointing to, means this psi state is currently is being, so this circuit diagram is currently being explained. So
Yeah.
it would have been better like I had a cursor here, but yeah. um Anyway, so proceeding ahead, so this tensor product state at AA, you can write in terms of this. So psi into state, the you cannot write a Bell state into tensor product, a separate tensor protected form. So that is nothing but that entanglement criteria coming to the picture, because it doesn't have exclusively 1 0 and a 0 1 in between that gate. So you cannot represent write in terms of tensor A, I mean a separate separated state. So that is why you have to represent the Bell state in a single entanglement form itself. So and then you're tensor producing the psi state with this with this Bell state. You're getting that at AA point. So this state, what is written is nothing but the state at AA. So what state you want to basically send from Alice to Bob is this state, alpha 0, this state. It would be better if I join from laptop. So it would be better for understanding for you. Just give me a sec.
Okay, sure.
Oh, wait. No. Yeah, our cat just went outside and there is fighting going on. So, yeah, I'm not able to see the mail here. Just one sec. Quantum formalisms. Yeah, this. But okay, hi Vitan. So could you please share me the link again? Like I don't know what exactly happened. I'm able to see the quantum formalisms link, but WhatsApp is also fine. Okay. Huh? Meetings. Yeah, Britam, if you would kindly share the link again. I don't know, so it's not showing here in the mail.
Hello.
Yeah, Britan, if you could kindly share me the link again here on WhatsApp.
Meet link.
Yeah, the meet link. By some I don't know. The in this Gmail which I open on laptop, it's not showing the exact same. It's just only showing quantum formalisms. What happened?
Okay. So on your WhatsApp you want, right?
Yeah.
Okay. Yeah, I have sent it.
Okay. Yeah, it's just taking time. I don't know. Um, the problem. Okay. Yeah. Okay. Finally, it opened. Cool. Thank you. Yeah. For some reason or another, like now the WhatsApp is open. The Google Meet is taking time to like open. I don't know what's the issue. Yeah. So, like Aditya, I hope it is okay for me to
Yeah,
proceed.
yeah.
And
You can continue.
that's fine. Then. Okay. So this state we were at this point that this state Alice has to send to the Bob. So this second point is I'm what is pointing at like this alpha 0 plus beta ket 1. So this state, if you write this state at A point, this will be the state. At fourth point it's written at A, this will be the state. So you just have to tensor product. That's the basic linear algebra. Then at 1 1 after application of C naught gate, you can directly get it from here itself. Like if the first qubit state is 1, then only the target qubit state will change. So first state will be the same, first term, this term will be the same. Fourth point, first term, alpha 0 0 term will be same. The second term will be changed, as in the second step will be undergoing 1 1 and 0, then the subsequent changes. So you are aware about the C not get operation. So after this application will get the state as 1 1. Then this Hadamard gate you are applying, so it will undergo again 1 by root 2, like the multiplication of that gate, or it will undergo a pi by 8 rotation in the two qubit space, or 1 qubit space, Hilbert space. So exactly, if you know. So this state after application of Hadamard gate will be getting this 2 state. And if you observe this, now this state has been separated. So why it is separated exactly? Because whatever gate you have prepared, like prepared the bell state, like whatever unitary gate you have used for preparing the bell state, that is used in reverse order. So by the basics of like quantum computing, you are aware that all the unit operations are reversible. So if you are changing the order of the gates, what state you will be getting, that is nothing but a separated state. So this state, as in this state 0 0, is the state so this is the combined state at 2 point that Alice is thinking. Now we move on to the measurement. So if Alice measures 0 0 state, the state we are now at the fourth point, and then this 2 2 section, 2 2 is written here, right? So this, if Alice measures 0 0 state, alpha 0 plus beta 1 is the state that Bob will get, right? So that
Yeah.
is the, yeah, so that is the state like Alice wants to send to Bob. But if Alice measures 0 1, then this is the state that Bob will get. If Alice measures 1 0, then this. But these states, if you look into alpha 1 plus beta 0, can be mapped into a bit error. So because alpha, the probability amplitude alpha should be associated a zero value, it's associating a value that is equal to 1. So that is having a bit error. So for this purpose only, a classical communication is required, as in the Alice has to communicate to Bob what her measurements exactly are. So if as per that, Bob applies a transformation of unitary. As in this operations, whatever Bob is applying from his end, right? So if it is 0 1, then Bob applies an X gate. If it is the 1 0, then Bob applies a Z gate. If it is the last state, then Bob applies both X and Z gate to get the psi state from Alice. So that is an operation or classical communication is required for. So hope this point is totally clear. Like it's written in below form itself, like all the details. Yeah. So so this psi state is what Alice wants to send to Bob. So this psi state will have a classical information encoded in it, as in classical information encoded in its probability amplitudes, alpha and beta, some form of information that Alice and Bob, before having that distance, has been pre-communicated. Like what is that encoding that we'll be doing? So for following that encoding, to encode your information, classical information into this, you can use a super dense coding approach as well, but that's the application oriented part of this. Okay, so this it's just the basics. So hope this is clear. We'll move on to our actual project implementation, what we are expecting. So if you look into this, here itself you'll get the idea, like why the classical communication is required. Because there are three more states in this that Bob doesn't know which measurement Alice got and then which state he has. So that is why this operation is needed, right? So the classical communication needed. So for removing, if you want to actually remove the classical communications, like what you can do basically is like first approach. We'll come to our first approach. What you can basically do is uh, can we find this instead of C naught and a Hadamard, a different unitary circuit such that the states produced, irrespective of the Alice measurement, are this, as in alpha 0 plus beta 1, alpha 0 plus beta 1, alpha 0 plus beta 1, alpha 0 plus beta 1. That's a highly unlikely case, but it has been observed that if you use, as in after implementation, it has been observed that if you use a non-unitary transformation here, as in a C naught and a Hadamard gate here, and some non-unitary instead of unitary, then that loss of information or that open system information will have a fidelity after output. If you look into code as we'll go through that, they will have a fidelity close equal to 1. Yeah, after implementation of this, it has been optimal. Okay, so yeah, so that is one of the way to avoid classical communication. Second is instead of this, so that is a highly unlikely case if you're using unitary, because any other circuit apart from C naught and Hadamard, even if for this you apply brute force, as in brute force means what exactly? What you can do is basically you can train an ML system. So you can convert this into just a matrix vector multiplication kind of setting, and instead of this C naught gate and instead of this Hadamard gate, what you are using here, you can take an unitary which has the 4 elements, and that 4 elements will have constraints of unitary, and second constraints are that the output state produced should be this, as in before measurement itself, whatever at 2 2 state you're getting, right, that 2 2 state should be this alpha 0 plus beta 1, alpha 0 plus beta 1 in all the cases, irrespective of Alice's measurement. So is there a unitary? That is what our first case implies. That's a brute force approach. And the second thing is that can we post process, as in there would be some kind of let's say Alice and Bob are many miles apart, that light distance, as in 3 into 10 raised to meter per 8 meter per second distance, what is covered by light in one say second, Bob is quite far from that. Let's say they are like planets apart, and light takes some kind of minutes to go from one location to another location. And in that period, like there is some like phenomena, some stars elements or something that Alice and Bobs are using to communicate, or some time adjustment is there. So Alice pre-communicates to Bob, at this time I will measure my state or my qubits, and then after that Bob knows that Alice has measured her state. Then Bob has to infer. So whatever state is there, like alpha 0 plus beta 1 or these other four states are already present at Bob's location. So now Bob has to infer like which unitary to apply on his to get the actual state that the Alice sent, right? So for that, what he can do is can he perform some kind of weak measurement, and can after that weak measurement is what exactly? Minimizing the disturbance to this state without actually measuring that state, applying some kind of transformation onto the ancilla qubits to get information about this alpha and beta amplitudes. So using that minimal information, can Bob infer without actually disturbing his state that what is the operation or what is the unitary that Bob has to apply on his state to get this state back. That is the second implementation. So for that, as in that inferences by weak measurement, what we'll get, right, with minimally disturbing this original state, that inferences can be, or that data can be measured, and that measurement can be used to train let's say a ML model or a reinforcement learning model to map the whatever states we got after measurement to certain unitary transformation that Bob can apply. So these unitaries are limited for now. For 2 qubit state or 3 qubit state, they are limited. They are limited to what? X, Z, and XZ combination. So these are the 3 sets of unitary. Now what we are going to do using this weak measurement, we are assigning a probability amplitudes of A, B and C, let's say, and root of A square plus B square plus C square is equal to 1 to the unitary gates. So first X will have certain kind of probability amplitude, Z will have certain kind of probability amplitude, and XZ will have certain kind of probability amplitude for after inferencing what the weak measurement is. This A, B, C's are basically you can say ascend the probability amplitude, the exact probability amplitude. So after this, Bob will get to know based on the weak measurement itself what is his A value, what is his B value, and what is his C value. So which unitary transformation he has to apply on his state to get this state back, alpha 0 plus beta 1. That is the second thought process. So in this case, what one can argue is the ML model what will be training will require certain kind of time to run or to infer that information. So that amount of time is basically it's lesser than that. In that case, what we can do is increase the distance between Alice and Bob, such that whatever time is required for reinforcement learning or other ML models to infer that information is greater than as in is you can say lesser than what's the actual speed of light is to cover that distance between Alice and Bob. So hope this point is clear. So this is the thought process that we are moving forward with. So you will have to research about what kind of weak measurements we can apply that to get the measurement values into subsequent ancilla qubits such that it will minimally disturb the state, and then whatever the measurements you got, those measurements will be used for training an ML model that will decide the probability amplitudes of which unitary gates you have to apply. But again, one can argue that this is only for 2 qubit state, so you can send an alpha 0 plus beta 1, but so alpha and beta can cover any kind of amplitude. So one can argue that you can use this circuit itself to send infinite finite amount of data, as in you can encode your state again using alpha and beta amplitudes, a second information, third information, like that. If you're getting the point. So this itself can act as a same like you don't have to increase the qubit, but our implementation, what we did is using the inference thing, like instead of using this as C0 and Hadamard gate, we increase the qubit size. As in, instead of just keeping the Alice's qubits limited to 2 set, we have increased that to like a value that is 8. I think we'll look into the next talk. So hope this point is totally clear what we're trying to do. So like if you're aware of this basic implementation itself, right, so this also can be used as a project itself. You don't have to go into that 8 qubits whatever you implemented, because this will be complex for you. It will be computationally extensive as well. And instead of that, you can use this. So hope this idea is clear, right? Because you have the exclusive set of what unitaries you have 3. In that case, in the second case, you will have 255 unitaries, and you don't know exactly what those unitaries are. This unitaries you have exact information about. So those unitaries, how to find, that is again a different kind of research that you'll have to do. So how to scale it to larger number of qubits. So in that case, what we can do is send larger amount of information. In that case, super dense coding will come into the picture, like how to send larger amount of classical information using those quantum qubits itself, how to encode our classical information in that alpha and beta value. So yeah, so moving on to the next document. Yeah, this. Yeah, is this possible? Only implementation will tell, and that kind of peak measurement is possible to infer the data, and that ML model should give that accurate inference of which unitary get to apply. So that will depend on that implementation. Hence, potential word is written. We are not by any way misleading someone. Like this implementation will 100% give faster than implementation. This is a thought process to avoid that classical channel communication. There may be other ways, but measurement is such a thing that it destroys the you will get the information about the system in a single measurement, not the complete information, a single information. But for getting that information, you have to destroy that state itself. That's what the measurement or a discrete measurement basically concept is. So instead of that, we are applying weak measurements to infer that. So the minimum amount of information to infer, such that we can train the ABC values. Okay, fine. Now this is the second implementation. If you look into here, what we have done basically is increase the input size. So we are trying based on that inferences to scale it to m qubits. So Alice has her n qubit state. There is an entanglement state between Alice and Bob that will be having a qubits assigned to it as 2m. So this is an n qubit state. This is a 2m qubit state. As in, what I'm pointing out is that this first set of Alice are nothing but your m qubits. Then entangled set between Alice and Bob's are nothing but 2m qubits. So it would have been better there when cursor, but anyway. So this okay, fine. Now, like we already know, whatever operation you're thinking about in terms of quantum computing, those will come in terms of U3 with 3 parameterizations and C0 with 2 parameterizations, right? Because you can write any quantum circuit into that tensor product state. So what you can basically do is, instead of, so since we have scaled it to right higher qubits value, so how many qubits are there for our implementations? We have taken exclusively 4 qubits that Alice has. So there are like total 12 qubits, and since in the single state like that Alice wants to send to Bob, so you did not need to worry about the computational power, because 4096 is a very less value, as in terms of vector, the 2 raised to 12 value, that 4096 vector what you'll get at the input, that's a very less value, and you can perform the computation on your laptop itself. So no need to worry about that. So yeah, 4096 edition, but you can limit it to 2 qubits itself. Like that can also be done if you don't have that kind of compute power. So what basically then 2 qubits, so Alice will have 2 qubits, Bob, and the entangled state will be a 4 qubit state based on the inference what we are getting from the POs. Okay, then the coming to this point. So this unitary, what is written, the unitary block what you have taken, that C0 and the Hadamard gate, that is a reverse operation what we are getting from that entanglement state, right? That operation we are trying to find by a brute force approach here. As in, brute force means what? Machine learning approach. The machine learning approach, what we are trying to do basically is, we know the output states of what the Alice we want. As in, based on the inferences, what the output state of Alice we want are, these are nothing but these states. So at AA, all the states are 0. You will have your quantum encoded classical data here that Alice want to send. So maybe it may be in the form of image, or maybe in form of some other kind of data that Alice wants to send, and it will be vectorized, and you already are aware about what is the quantum encoded classical data based on the 6 encodings that we have discussed. So after encoding that, this is the state, the Siam state that Alice want to send to Bob. Okay? So at 1 1, what you will have is this Siam into the entangled state between Alice and Bob. Now this is again the second kind of research. So that is why, like scaling based on the inference to higher number of qubits is like likely to be avoided, because for 7 qubits you cannot find an entanglement entangled state. So that's well, you can find 2-3 sources of paper based on this statement as well. But this is for 8 qubit, and we are again using a brute force approach for this. So so how to find an entanglement state for increased number of qubits apart from increasing by the number, like let's say above number 3. So for number 3 we have GHZ states, but what about number 4, what about number 5, what about number 6, what about number 7, what about number 8 that is implemented here? So that is a different research. What we have basically used is an ML approach again, based on based on what, based on the 4-5 evolutions of the entanglement what we already know. So how to evaluate whether the given state. Yeah.
Say, I have a question. So we are saying that for 4 qubits, we cannot generate an entanglement.
No, for 7 qubits, 7, not 4, 7. For
Seven
for
qubit is
4.
also possible.
So 7 qubit entanglement state, as in if you'll find in the literature, the 7 qubit entanglement state is not satisfying the criteria. So there is one particular criteria, a maximally separated entanglement state. That is what we require here. A Bell state is maximally separated entanglement state. You can have an entanglement state for 7 qubit, but that criteria of maximally separated entanglement state, there is a specific name for it. Yeah, there is a name written, it's way back, but there is specific name for it. So that state is not possible for 7 qubit, particularly that case. So you can have you can have a Google thing, but type in for 7 qubits entanglement state, the papers will come in Google call itself.
Okay, okay. I will have to check that one. Okay.
Yeah, sure. So yeah, what you said is correct, Bitan. Like 7 qubit entanglement state is possible, but a particular state what we require for teleportation criteria based on the inference of Bell state, the Bell state which is maximally separated state, that state for reproduction for 7 qubits is not possible. And even if there is 7 qubit state, like entanglement state, how are we going to distribute that? That's another research. So how many number of qubits should we keep to Alice? How many number of qubits should we keep to Bob? Like whether it be 3, whether it be 4, like that. So that will be again. So better to take an even number itself. So yeah.
Okay, got it, got it.
Yeah. Fine. Now, moving on with the circuit emulation. So we were at this unitary by SVD, ML, QNN, AABN, and QR decomposition. So you are already aware about the SVD technique by the ML technique. What will be the outputs of this? Basically, is based on the inference. This all the states, as in the first state, what the Alice had should have all the binary digits from 0 to 2 raised to m, all the states as in binary states, all the basis states if we in the 0 on basis. So the first state will be 000 up to 8, then the second state will be 001, like that. The last state will be 111, the state. So those states will have, each state will have what, certain kind of, like the state that Alice wants to send, as in what the state can be written, 00 will have this state psi m, and there will be some transformation. So that transformation is what exactly in the previous doc which you already know. It may be X transformation, it may be Z transformation, it may be original identity transformation, or it may be XZ transformation. But here, when you are increasing the number of qubits, we don't know what exactly that unitary transformation is. But what we know is a number, how many unitary transformations are possible. So for this case particularly, there are 255 unitary transformations possible based on the state what we'll be getting. Like hope this is clear. So this state I'm talking about, the at A2 is written here, such that two cases, this state I'm talking about, this state. So this state, all the basis states of 00001, like up to this last state, this psi 0 based on the inference will be a original state what Alice wants to send to Bob. But this state 001 0010 and the last state 111, that states what transformation will have to undergo, that you will have to research from your own. So that is why it was like the thought process came like it is better to implement what we already know, because the three cases in the previous three cases of unitary we already know what to apply, but here we don't know what to apply onto the Bob. So Bob can have a inference, he can apply his machine learning itself on that weak measurement whatever he'll get. And like there is one more thing, like if you'll increase the number of qubits onto the Bob side, then the weak measurement, what kind of weak measurement, now how many ancillary qubits you have to like incorporate here to get the sufficient amount of weak measurement information to train your ML model. So that is also another thing. So there are 2-3 criteria here, but if you'll find, so what you can do is basically use a brute force approach for that thing as well. So what you can do is apply, so you can find the unitary itself, right? So based on the state, what you will get at psi, but so there is one more thing of a conflict here. You don't know what is psi 1, you don't know what is psi 2, you don't know what is psi 2m. So how to train your ML model, what to back propagate exactly, what state to back propagate. So that is also a point. So for first case, what we did is we took a mean, as in what we state, accurate state. What Bob wants is this state, right? So what we did basically, is there a unitary such that this state is repeated? Like instead of psi 1, some transformation, unitary transformation on psi, like psi 0. We have taken for training purposes psi 1 also to be psi 0, psi 2 also to be psi 0, psi 2 m minus 1 also to be psi 0. We know that exactly a unitary transformation cannot do this. If it would have been possible, then people would have already implemented it for quantum teleportation for 2 qubits as well, right? But this unitary is not possible, but we are trying that as a case 1. So that unitary by brute force, is it there? So if it is not there, then keeping the state at psi 0, what are the remaining states you get? That states are nothing but your actual states, what you will be getting. So hope this point is clear. After finding that unitary, after applying that unitary tensor protected with y, if you write this state in this form, this state, what you will get, psi 0 is fine, first we already know, but if it's the second state, if it is psi 1, psi 2, psi 3, that will be different from your psi 0, right? So that, what that state is after finding that unitary, that can be your inference basis for finding the unitaries. Like after applying your what kind of unitary transformation you have to apply on psi 0 to get that psi 1, what kind of unitary transformation apply on psi 0 to get that psi 2, what kind of unitary transformation to apply that on the psi 0 to get that subsequent states. So that will form your basis of x, y, and so x, z and xz here. So those will be 255 numbers. So how to find again that? You can use SPD approach, you can use ML approach. So basically what we're trying to do here is, what we're saying here is, if Bob has sufficient amount of information and he already has the set of unitaries, what he can transform the state after the Alice send his state, her state to Bob, then if has that sufficient information, so he can apply that information without that classical channel communication between the Bob. And how to get that information is basically using weak measurement. So that is our whole research point of view here. So yeah. So that weak measurement basically is your research criteria to research on your own. You can ask us queries as well based on that. But hope the you can say a detailed overview of the project is clear.
Yeah.
Yeah. Okay. Then moving on. So this will be our type 1. In which case we have taken the psi 1, psi 2, psi 3 and subsequent psi m to be same, and then found that unitary. And you will find that if you implement non-unitary, the fidelity values of this state with the actual state, what we have given it, that state is nearly equal to 1, that fidelity values. But again, the research criteria here is like to what fidelity value it is 1. If it is float 64, if it is float 32, then if it is 1, then again you have to check that. Means if it is float 64, it is 1. But if your scaling of the quantum state is to the level of e to the minus 10, e to the minus 15, and that information which you want to send, so it will naturally give the fidelity 1, but in actuality case, that information, the state what will get or what will be produced will be different from your size 0. So that also you have to print and check. So yeah, that's a different thing. Yeah. Okay. And this so this what we discussed, right? This is your type 2, in which case the psi bob is we have taken that as a same. So this is your type 2, and the type 1 is this. So yeah, so it's written here, you can go through. In this case, if you want to remove the need of the classical communication channel, we can apply unselect qubits on Bob case, which can perform a weak measurement on Bob state without disturbing the Bob state, using which we can train a neural network or an RL model to get an inference on what set of basis or what set of probability amplitudes we can apply on the unitaries to get to know to Bob which unitary to apply from his end. So what should Bob have previously? Bob should have the state of transformations, like this unitaries he should have, or he should know exactly what unitary to apply. So this 255 set of unitaries information he should already have in that case. So yeah. And the above two cases in short notation. So you can go through this. This is the above two implementation in short notation format. Yeah. Okay, fine. Then we'll move on with the code. So hope this implementation is clear.
Yeah, yeah.
Like this detailed introduction is clear. So like again, so Aditi, this is a thought process, and this is on a piece of paper. We can exactly write like weak page on it is possible, but for actual inference and then actual training of that ML model, so that information whether it is sufficient to train a neural network model, what information loss is needed from Bob's qubit, that is sufficient for A and B values to be exact what we require, as in to get that inference. So that is comes under implementation. So hope this is clear, because whatever weak measurement will do now, it will have some kind of impact on the state of Bob. It doesn't happen like it will not have certain, like it will not have impact. So there will be some information loss on the state which Bob has. So that is another thing. So yeah. Could you please kindly share the code from your end?
I hope my screen is visible, right?
Yeah. So it is visible. Yeah. So you can go through this first code block, whatever tasks are written here. So implement various other quantum encodings for this. So what we are trying to send is basically, so we are at the first block itself, the comments section. Yeah, first
Yeah.
block. Yeah. So second thing is below is the amplitude encoding implementations. Fine. The study the implementation code as well as refer the architecture given in Heisenberg quantum AI document. Fine. And incorporation of the super decoding, Holloway bound, Shannon limit here for maximizing the classical information. This 4 point you can ignore for now, because what we are trying to basically do is getting to work that algorithm what we have discussed. So if that is working, then this is the optimization stage which we can do later. And like what kind of information which you want to send can be like maximally means like optimized to send in minimum number of qubits. So no need to do that for now. So anyways, so this is your first cloud. So now we're at the first level. What we are basically doing here is amplitude encoding your image data set. So this train images and train labels, which this code is already been discussed, right? So this, yeah, we are separating that into images and labels, because as in 5,000, 5,000, 5,000, we are separating that. And then this is nothing but you're resizing that images. So first, so this is nothing but the resizing 28, 28 to a new value. This is also fine. And then you're converting that to list to, and appending that all the values to that particular list, then converting that to an array format in this, and reshaping it to value that is so this in this case is no, this below n is equal to 4, right? This n
Yeah.
is equal to 4. Yeah. So basically what we are trying to send here is having a value of 16, which will take so whatever image you're trying to send, it is a 4x4 image, which is having a requirement of 4 qubits to be sent to Bob. So yeah, hope this is clear. And you're taking just one of that image, so you don't need to do all the code. Just one zero implementation or one implementation is also fine. So just code, the same code is taken here, what you already know. But just a single state is fine. You don't need to do all this. Fine. Yeah. So this again is redundant here.
So the we don't have to look into this, right? Like implement various other quantum encodings.
Yeah, quantum encodings, as in for whatever state you want to send, you can look into other encoding, right?
Okay, okay.
Yeah. So,
Penny Lane, are we using some software or should we do it from scratch? Because from what I can see here, it has been just used. We have just
yeah.
used.
The Penguin already has method definitions defined for
Yeah.
amplitude encoding, phase encoding, but we have our two more encodings, right? It doesn't have for a function defined for unitary encoding. And even if it does, it's only for QSV architecture. Second thing is it doesn't have a function implemented for novel density matrix encoding, and it doesn't have for one more encoding. I think binary encoding is also not there. So you'll have to implement that from scratch. So better to use, and it will be coherent or it will be consistent with the code used below, because we have been constantly following torch library for this, as in NumPy library or torch library, PyTorch library. Or in some cases, in rare cases, whenever neural network is implemented, we are following TensorFlow, but that's a rare case for you guys. Unit is used only one of the code. So better to have this, like, so what exactly Qiskit library does, what exactly Penguin library does, apply some kind of C++ compiler to whatever code we have written here. So basically, they are optimizing that to have minimum runtime. Nothing else is different from our end. Like,
Right.
so the same implementation is there. So yeah, and because this implementation, if you'll do, you can use your conventional training libraries, as in PyTorch is a conventional machine learning training library which you can write a code. So that has been around. So better to like not go for quantum libraries like Pennylen, in which case we'll have to adjust to whatever format they have used. In that case, and also some integrations are not possible. So this was the research done probably looking itself, but some integrations are not possible for optimizing that quantum circuit. And in that case, when you're using Pennylen, you have to exactly define the circuit, the unitary. So how you have to use our procedure first, find that unitary, then you have to transfile it, and then you have to like use there. So and subsequent trainings will be more difficult. And the second thing is whatever code is implemented here, that is the best version.
Hello.
Yeah, hello.
Yeah, your voice is it's like not properly audible.
Okay. From which point it is?
I think this is fine. Yeah, you
Yeah.
were
Oh,
talking. Yeah.
yeah. So like, if you're using Pennylen or Qiskit or other libraries, some integrations are not possible. As in, you have to exactly define the circuit what you want to optimize the parameters, and it will be limited to RX, RY, RZ gates. In some cases, you have to manually implement U3 and C0 rotations. So that implementation or that parametration is not possible in some cases, and so better to use whatever libraries are already existing for getting that ML optimization. Or so what we are doing there basically is the same thing what we are doing here, using ML back propagation. So their back propagation algorithm is different from here, as in they have been using either a parameter shift rule, which is having a less computational cost than compared to here. But again, like, there are limitations based on whatever circuit you're using, RX, RY, RZ, and whatever depth you're limited to, you'll get that amount of unitary after parametrization. As in, it will be an inferior method to what we are using here, as in the actual QR decomposition or the SVD decomposition or other like ML. So hope this point is clear. So yeah, moving on, yeah.
Okay.
But like that research, why it is needed? So to give the positive side of the Pennylen cascade, why that research is needed? Because after a certain period of time, so we have our other methods, like there are other projects how to get that unitary circuit for have a scale that is above classical computational limit. So for that case, that research is also needed, because you have to parameterize those gate for increasing the number of qubits. So what kind of result does it get, like do we get? So VQ implementation, people have been trying for 128 qubits. So that implementation result, that back propagation optimization itself is happening in the U3 and the C0 gates, as in the U3 gates or the RX gates. So that research is also needed to get that inference for one-to-one mapping for a state that is above the classical computer limit. But here we are limiting to quantum inspired approach. So like a dot library is fine. So yeah. Okay. So this implementation is basically like what we're doing is defining this class, and we are trying to find a state, a quantum entanglement state that is minimized based on 4 5 criteria that have been discussed there. So if you go to the code, like this is a complex state, it will have a real part and imaginary part, and those are defined in the cell params. So whatever 2 raised to 8 params we have, in that params, the first half is given for the real part, and the second half is given for the imaginary part. Yeah. So this compute reduced density matrix. So this basically what this implementation does is, okay. Yeah. Uh, Yeah, so there are like 4 5 criteria which you can infer based on whether your state is entangled state or not. So that criteria are used there. So one is what trace reducing of the density matrix. So how to trace reduce a density matrix you will be aware about. So if you can, so what exactly the criteria is finding for maximally entangled state is if you can take your entangled state, divide it to half, as in half the Hilbert space, and whatever state you will be getting, the density matrix of that state should satisfy the reduced density matrix of that state should satisfy the trace of that row should be equal to
Right.
the value that is like 1. The trace of the row square value should be equal to 1. I think so.
Hmm.
Yeah, so that's one of the criteria for getting that state, whether it is an entangled state or not. So like that, this is the second criteria. So this is compute. So this compute density matrix is a function that is implemented in one of the criteria. So this is called here that function, and then this is one of the criteria. There are other criteria as well. So Smith decomposition is one of the criteria to get to know
Right.
whether the state is entangled or not. So yeah, so this criteria, it has been this is used as a you can say a loss function here to find the state
Right.
after backpropagation to optimize this loss such that uh, the as in after getting that optimized stage, the this criteria of entanglement is satisfied. So hope this abstraction level of either we'll have to go into details of all the criteria, entanglement criteria, how to identify that, but that will be a longer discussion. So that you can keep it as an kind of notebook kind of setting and keep it as an abstract level of information that we already have that state, that entanglement state here, and you did not hit. So that is why I wanted to avoid this discussion. What you can do is what state we already know, that is your bell state, right? So instead of doing all this, just take that 2 cross 2 matrix, that not 2 cross yeah, just take that single qubit state which you want to send. That will not be image will not be possible, but just take a single state alpha 0 plus beta 1, and then you can use this state to send then to implement our project itself. So you need not need to do this, but that is also fine because this is you can keep it as a back box for now.
Okay.
Okay, fine.
Yeah.
Yeah, so yeah. Yeah,
Verify.
and this is again a verification of the entanglement state. So this again, you'll have to specifically see the ranges of what exactly is the value or the index as the element value you're getting, and what is the level of precision you have been implementing in that. So this code has been implemented for flow 32 precision. So that level of you'll have to check the accuracy as well because this verify entanglement criteria is satisfied for certain range. So
Hello.
whether your
Hello.
element range is above that, then it will be not. So whatever. So you look into verify entanglement stage and get to the below. So this AME I was talking about, Britan. AME. So AME is nothing but maximally separated entangled state. So perfect AME. If you go below,
Hello, Akshay. If you don't
yeah.
mind, like your voice again, it's like sound very distant and it's not possible to make out the words.
Okay, okay. So if you look into the scrollable element, you can print go into right the scrollable element, the scrollable element.
Yeah.
Yeah. So if you look into the verify entanglement criteria, so this entropy value for that 4 qubit reduction, what you are getting from the state which is produced, this is satisfying the target value criteria, as in it's near to that to certain level of precision. So if you look into the purity value, what you are getting, the trace of row square value, what you are getting, and the Shannon entropy value, what you are getting, those are nothing but your evaluation criteria used here, and they are nearer to the target value. So this is again a brute force approach that you are using. So based on the loss function, that is the reduced density matrix, that is the sole criteria for getting the state as evaluating the state whether the given state is entangled or not. Based on that criteria, we have that as a loss function. We have backpropagated that loss and minimized that loss such that we'll get a state. And now these are the evaluation criteria. These are other evaluation criteria. You can incorporate this into the loss function as well to get a more optimized state. But this evaluation criteria, what it tells us, whatever state we have, after getting after this entropy value, should be having a target 4. It's having this 4-qubit reduced entropy state should be having a target value 4. It's having a entropy value of 3.80. So it's near to the target state. So this implies that whatever state we have is nearly AM, nearly maximal entanglement state. So hope this discussion is to some aspect. Hello, Aditya.
Yeah. Your voice was not audible actually. Yeah.
Still not audible.
It's audible now.
Okay. Okay.
Yeah.
Fine. Okay.
We
Cool.
discussed this,
So
right? After that, did you say anything else? Or?
yeah, we discussed this entropy and purity values.
Yeah,
So
yeah.
were you listening to that? Were not?
Yeah, I listened to that, but after discussing this is almost nearly an Amy, I think I did not hear anything.
Okay, yeah. Then I was asking the question like whether this point of clear. So moving on,
Yeah.
like So like whatever discussion we had, right? This discussion is implemented here. So whatever ket psi which we want to send, this ket psi is one of the state that Alice want to send to Bob. So that ket psi state is nothing but okay. Just a sec. The input qubit of the input state of the 12 qubits, 8 on Alice and 4 on the Bob. So what state you have is the 4-qubit state that Alice has, right? That state. But that state needs to be chronicle producted with the state what you have after this above code, right? This state. So this will be a 12-qubit state that will have a 4096, and this will be your section wise 2 section. That will be your state. Okay. Hope this implementation is clear. Then yeah, so that is nothing but a chronicle product that is done. And the next part comes is this implementation. So this implementation is like what you have to focus on, but this implementation again, so if this implementation will explain, you can keep it at the back of your like mind, because this unitary what you're finding by a brute force approach here, so you can use whether SVD criteria, whether you can use a QR criteria, that is also fine. So you will be like you are already aware about the code. So what exactly is the code here? Like you're taking the input like vector, that is your state above. So if you go into above section, can you please go into above section? Yeah, so this input state of quantum teleportation protocol, this is your like state which is the total state, right? So this is your input vector. What is the output vector which you want? Based on the 2 cases what we discussed, the output vector what we want is that, like, this is one first case in which the output vector is the tensor product, a summation of the tensor product of the basis state uh, of the qubits the Alice has, tensor producted with the state which the Alice wants to send. In the summation of that state is already been discussed, right? In the doc also it has been discussed in 2 cases, and in that case we are taking the ideal case that Alice want to send to Bob as the output vector, output state, as in this ket psi.
Right.
Ket psi, that state what Alice want to send, right? That is nothing but the output state taken here, the 4 qubits based on the Bob has, right? So this class unitary, what does it imply basically is, so this is a superposition that is called, then we are taking the cell dot u, the section of the parameters in that. So those parameter values are in 256, 256 values, which will be decided based on whatever output state we want. The forward section is like discussed here. So this will have you can say we have discussed that architecture, right? It will be a chronicle product of whatever parameterization self dot you have with an entry operation to get your unitary cron I. So that will be your total unitary, right? So hope this point is clear. And then what you're returning basically from here is your whatever output like unitary matrix you are trained multiplied by the input vector what you have. So that will give you your output vector, and that will have a length of 4096. But what is required for your end, as you don't require all the 4096 values, because you already know the above values will be in the basic states of zeros and one. So what you require here basically is the 4 states, the last 4 states. Okay, so fine. So this, hope this first code block is clear. The define initialization section is clear, define forward section is clear. Then this Frobenius norm section, what this basically does is defines a loss function. So like yesterday, so this output state is written here, right? In the comment section, you can go through what this state is. So this state is what we're trying to get here. as in this is the output state which it requires. So this 0, 0, 0 is nothing but our state that Alice has after undergoing that unitary transformation tensor rotated with the psi 0 plus this state what the Alice has tensor rotated with psi 1, this state what the Alice has tensor rotated. So this all basis state with the state that which we want to send. But what we don't know exactly is after this psi 0 which the Alice want to actually send, we don't know the psi 1, psi 2, psi 25. So what we're doing here is we are taking a state psi 0 as the actual state. So what we are actually training the circuit for is psi 0, psi 0, psi 0, psi 0. All the subsequent should be psi 0s. So that is what we're training the circuit for. So this is nothing but predictor.view. So what this predictor.view it changes the shape of your output vector. As in 4096 vector, it changes the shape to 256, 16. So what this 256, 16 entangle like tells us basically is this 256 are nothing but the numbers, like how many numbers of states you have. So this 256 is nothing but this first 0, 0, 0, 0. Then like in that 0, if the zeros number if you consider that. And this 16 what it implies is for the first number that is this 0, 0, 0, 0, what is the state you have, that the psi 0 state. So this reshaping essentially does that. So once you have that reshaping done, so this loss function is written here. So loss is equal to 0 for I in y. This we are first normalizing that y, normalizing that I, whatever you get, as in what this I will be, this will be all the psi 0, psi 1, psi 2, psi 3 up to psi 55. So we don't know whether it is optimal like normalization or not. So we are incorporating that here because these are a parameter here, as in after multiplying that with the unity operator. So we are defining the make unit operator here, as in we are defining that okay, okay, fine. So one more thing you have to incorporate here, this unitary is not a you can consider this unitary as not a unitary itself, because we have never defined a function that makes it unitary. So what you can do is define a function. Please go above. Yeah, please go above. You can define a function here itself, make unitary, and in that function what you can do is you can decompose this self.u into three sections, and then take the multiplication of the two eigenvalue matrices. Or second thing is to make the QR decomposition. QR decomposition is better because sometimes SPD gives the list it doesn't optimize in the limited set of parameters. So limited set of iteration. So that is why you can use a QR decomposition. So you will be sure shot like whatever unitary you have, it will be a unitary, as in it will not be a non-unitary matrix, or it will not be a randomly initialized matrix. So hope that point is clear. Then yeah, so you'll have to define that function. So it is clear, right? That's a simple definition you have to take. The simple definition, make unitary, self pass the self. Then what you can do is return some return function you can write. Before that, what you can write is that value. So if suppose you are returning m, so that m you have to write, and then what you can do is np.linearg.svd or np.linearg.qr, and then pass on that two values, or pass on this self.u value in there, and then that m and you'll have to return one, not return, you have to put in one more definition, not definition there, put in one more variable there, m comma the upper triangular matrix what you'll get, but you'll return only m. So that will essentially imply that when you call that m unitary function, it will make the matrix unitary. But this implementation essentially means that the matrix is non-unitary. Okay, fine. And this Frobenius norm condition will move on to this for loss section. If it is 0 for I in y, what we are essentially doing here is I is equal to I divided by torch norm of I. So this essentially means that we are normalizing the state, as in whatever 16 states you have, psi 0, psi 1, psi 2 up to psi 255, you're normalizing that, because as already explained, the u is not unitary, so it will not preserve the norm. So that is why normalizing this. Then after normalizing, you're taking the torch norm. So this is our loss function. Essentially, you're taking the loss and then adding all the subsequent losses such that the index of first state if you take, and you subtract that from the state the which you all actually required. So this is your ket size. So this you have been saying from the start, right? The psi 0 is the state, is the ideal state. So that is nothing but the state you will be subtracting from all the i's. So that will be forming your loss function. That is written here, the Frobenius norm. So if you look into this, these are the other things that are tried, like it didn't work out. So that's why. So this is nothing but one of the loss function, right? If you look into below, there are like overlap, as in just a dot product is implemented here. So that you can try that as well. Some other loss function also you can try. And this was yeah. So before that, like there is another criteria that was tried here. So A can also be taken as superposed state. So so A, what is A here? You can look from the above. Like A is equal to y into ket psi dot conjugate dot y. So there is method of projection that was tried here. So you can try that as well. But this works fine. So you don't need to go for that method. And yeah. So could you go below? Yeah, so this is again a loss function, I think a learning rate scheduler that is implemented here. You can use a conventional reduce R element pattern. You did not need to go this, but this will perform better optimization from that. Okay, fine. And then go into that will be our go below that will be this will be a training loop, and it will find the unitaries and the like unitary or non-unitary that will map to your required ideal state. So and yeah, so after this you look into this is unitary, what the train unitary model u.data, you will get the train unitary back. This will be your identity function. Then you will have to check the unitary error. What is the unitary error after implementation? So since this is not unitary, you will find that the error rates are like very high. If you go into is this printed? Go above. Can you could yeah, this final unitary error, right? This final,
Yeah.
so this nothing but the loss is minimized. The main loss is minimized, and this final unitary error is very high because you have not implemented the like unitary criteria in the loss function as well and in the make unitary as well. So that loss is very high. And scrollable element, if you open this scrollable element, yeah. Yeah, only these things are invented. Okay, yeah, it will be below then. Yeah. So what we're essentially trying to, so this loss, what we have, right? 2.7 into 10 raised to minus 5. What you can do is, so this is multiplied here. So output vector, you are essentially, okay. Yeah. So, so this is your output vector. As in, what will be your output vector now? Is all the 4096 vector, right? That will be your output vector. So for getting that, whatever unitary you are trained, multiply that with the that with the identity and multiply that with the input state. That will be your output vector. Then whatever print output vector you can do, you can have a look at what is the scaling range here, and it's a defined as a complex thing, like complex numbers. Then we are reshaping the output vector to this format. Instead of measurement, we are reshaping here. So hope that thing is clear. So what this state basically mean is, if the measurement is first, then you'll get the first index out of this. If the measurement is second state of the Alice, you'll get the second state. So hope that thing is clear. So this is the state I was talking about. So what 256 in that, the first state is our ideal state that the Alice want to send. The subsequent state will be some unitary transformation that Bob has to perform from his end to get the original state that the Alice want to send, right? So you can calculate that from here itself. So whatever 256 6 states possible, like you can find the unitary from 0 to 255 by using the SVD approach again. So what you do basically is take the index first state, what output state or the ideal state that Alice want to send, take that, and you can apply SVD to get that unitary transformation. That will be a U0, that will be a U1 for the next iteration, that will be a U2, that will be a subsequent U2 255. So that all unitaries will form the unitaries that Bob can apply to get the state that Alice sent. So that is the thought process here. And then yeah, so this loss, various kind of losses are incorporated, like just printed here. It's not a training loop, just the losses. So what are the losses? Like to get an idea, we have tried printing it here. So there are tasks written here as well, like you can go through. So all the overlaps are 1. So better loss function is required to find the non-unitary that produces all the state equal to ket psi, implying that ket psi is separable state. So there is one more implication here. What the psi state, what it is there, irrespective of the Alice measurement, is received at Bob end. So that state becomes separable state. It's not entangled with the measurement that Alice is like performing. So what point I was trying to discuss here is, whatever after printing values you'll get, you'll have to figure it out manually, because again the scaling factors comes into picture. Even if the loss is 10 raised to minus 5, right? This state, if you look into, is in the range of like these values. Okay, these values are fine. As in, if the error loss is coming 10 raised to minus 5, right? These values are fine. 0.02188 value is fine, because like this doesn't have that kind of range. But if you increase the size of the qubits, then 10 raised to minus 5 error. So above error, what your main function you're getting, right? That 10 raised to minus 5 error. That error needs to be in this scale range. So for now, this is fine. You did not need to consider this 1 point. So there will be an error loss as in some error between this first element. So if you look into first element, 0.037 plus 1.19179 into 10 raised to minus 8, right? That error will be coming after 10 raised to minus 5. So this state will not be accurately sent. So this will have an error, which you can see later as well. So this state, what you have printed, so subsequent, so this state, these are all the state. So if you go ahead, if you go above, yeah. So we are printing all the i's in y, right? Ideally, all the i's in y should be same. Are they same? They are differing in amplitude as well, but they are nearly same. So there are like various criteria you can implement here are the same. Like you can try incorporating the Frobenius norm between arrays as well, but that will give a rough value. So you can try printing and checking itself. So there you can find some kind of difference, right? 0.0037 and 0.034. So it's having the same sign. It's still not okay. Yeah, it's having the same sign from the probability amplitude itself, but it's the second stage, it's differed because you're not having that kind of accuracy level achieved in the norm, like the loss function, because it tends to minus 5 limited. But the basic thing is what you can do is assume that these states are all same and you did not apply unitary state and take that one whatever state that Bob receives as the state. So that is the thought process. So and second thing is that this is a non-unitary implementation. So actually these values are to be near. I mean, these values are near to hai. लेकिन अगर unitary implement करें तो the values near भी नहीं होंगे. So there will be probability amplitudes might be same, but there will be other like you will have to implement it and see what those exact values are, because this is a research team. So hope this point is clear. Yeah. Then yeah. और फिर क्या है ये okay, this is the second implementation of same. So you have that, right? Yeah. So okay, so this has been done itself, so you do not need to do again. So this enforce unitary function is already done here. You do not need to do. I thought it's not implemented like this. So all the code remains the same. Everything is same. Just we are making the matrix unitary, nothing else. Right? Yeah. Okay, fine. And this also you can go through the comments written here, right? This comments. Go above. Can you kindly go above? Yeah, this all the comments are your tasks as well. So based on the training, some conclusions are written and some are the tasks. Okay. Okay. And yeah. So yeah, that's all from our end. It's the similar loss function, like what loss we are incorporating, that is implemented here. So yeah, so those are the two implementations. And what is expected from you to research on the weak measurement criteria. Then based on the results gotten from weak measurement, how we can apply a reinforcement learning or a neural network architecture to map those inferred data into the amplitudes ABC of this unitaries for the given state that Alice has sent, like that Bob has received from Alice's end. So hope this is clear.
Yeah.
Yeah. So like implementation wise also, if you look into, there might be a like precision loss. So this implementation did not be accurate. This is our first take on the problem statement. So like you can take your time, go through the details, work it out. If this implementation you don't have to work it, you can try implementing it for the basis like the first basic discussion what we had, right? That. So you can try that as well, right? Because that will be easier for you. Because that, and based on that only this has been inferred, and there are like losses here on the entanglement state as well.
Right.
After so that can be avoided because we know the exact circuit in that, and because we know the x, y, x, z, and x, z exactly in that case. So yeah, fine, cool. That's all from our end. And actually, like I have not been preparing for any of the lectures, but this was a surprise from Britan. Like yesterday we had a discussion on the sequences which we want to follow. So teleportation was specifically kept at last. So anyways, so discussion happened. Like please go through the like instructions given in the comment section. Please go through documents again. Hope the problem statement is clear. If it is not clear, you can watch this video again. And then whatever instructions are given in the video, like you can follow that as well and then implement it. So,
Sure.
So we'll be getting a recording of this session soon in 10-15 minutes.
Okay, sure.
Thanks.
Okay, thank
So
you.
is Britan there or he has left the meeting?
I don't think it's there.
Okay, sure. Okay. Chalo, thanks then.
Oh,
Bye.
thanks for the meeting. See you.